My name is Adam Faircloth. I'm the Australian Young Researcher Award recipient for 2019, and due to the pandemic, of course, was unable to attend the 2020 conference, which was postponed now. And here we are. So today I'm going to be presenting my my project topic on, if I can get the slide to change, the development of a non-destructive evaluation system for cross-laminated timber panels, which I presented back in 2019, but has made some progress since then. So I'm a timber engineer by trade, working with the Department of Agriculture and Fisheries, but I'm also a master's student with the Griffith University based in Gold Coast in Queensland. So this talk is going to mainly go through the background introduction to timber structures and timber engineering, leading into the aim of the project. So why we thought that this was needed for the industry, flowing into the method that we've adopted and developed, how we validated that method, results we got from that validation process, and the outcomes that we've gotten so far and expected benefits that this project has to the industry. So before we get too far into it, I would like to acknowledge the funding supplied for this project. So this is an Australian Research Council funded Centre for Future Timber Structures Hub project, facilitated by the University of Queensland, and of which there are a number of partners involved, such as XLAM, a mass panel manufacturer in Victoria, Hind Timbers based in Queensland, Griffith University, Lend-Lease, Orup, as well as the Department of Agriculture and Fisheries, my workplace. And from there, there's my supervisors on the right for my masters, which are Dr. Hassan Karampour, Dr. Stephen So, who are both senior lecturers at the Griffith University School of Engineering and Built Environment. Dr. Chandan Kumar, senior scientist at DAF. Dr. Loic Brancheroux, research scientist for the Centre for International Research and Agricultural Development in France. And Dr. Henry Belliers, product development manager at Hind Timbers. So wood-based mass panels are widely accepted and commonly used, becoming more commonly used, building material in substitute to concrete and steel, and a form of engineerable product that allows for the efficient construction and development of low to mid-rise timber structures. Of these products, there's a number of benefits to using them, but a few off the top of my head that I've got noted down here are the natural carbon sink properties, being a green product, as well as their proven health and well-being benefits to living and working within them. I guess their most interesting advantages would be their lightweight and cost-effective alternatives for construction. So lightweight is in timber is a lot lighter than using steel and concrete, and cost-effective is that the amount of trade needed and amount of tools and cranes needed to lift these panels and install them is considerably less than what you'd need for a concrete or steel composite structure. Another point on that, this project in particular at Kangaroo Point in Brisbane is situated above a transit tunnel known as the Clem 7. Because of its placement above a tunnel, there's a number of restrictions on its weight, as well as the depth of the foundations for the building. So this project really gave timber a chance to shine as being a really useful product for these kinds of applications. So within wood-based mass panels, there's a number of subcategories. So you've got, in this picture here on the left, is a building in 25 King Street, based in Brisbane. So the beams that run along the underneath the floor, your cross beams, they're made of glulam, which is a laminated beam product, which is beams laminated parallel to each other. And then a panel such system, which is cross-laminated timber panels, being used for the roof there, which I'll talk about in a moment. And then versions of those, such as NLT, nail laminated timber, and VBMP, veneer-based mass panels, and there's more. So from that, cross-laminated timber can be used across both as a ceiling, as you can see there, floors, of course, and also as a wall system, but is most suitable for its horizontal use due to the long spanning capacities that it has with its cross-directional layout, which we'll again talk about in a moment. These panels have limitless almost in terms of size. The only limit that you're going to have to deal with is how they're going to be taken on site on the truck. So into CLT as being the selected product for this this research project, being the real powerhouse for the mass timber market. We decided to really focus on it and how we can add more advantages to the manufacturing process. So CLT, as its name suggests, the cross-directional layering of each perpendicular layer being of each preceding layer being perpendicular to the last, reinforces it during a constant and during any kind of bending moment, giving a strong direction along the major axis and a slightly weaker one along the minor axis, similar to plywood. So the design of these structures encompassing CLT is more so governed by, rather than how strong it is, by the serviceability criteria. So from that, by knowing the elastic properties and shear moduli of the panel, we can determine the application for these products. So ways of determining these mechanical properties, there's two main ways that industry goes about using them, as well as academia. One of which being a pre-manufacturing or averaging process, where the panel is taken and the individual boards within the panel are averaged together after being non-destructively graded, averaged together into the panel to give an average result for each axial direction, which, while gives a good estimation of the panel properties, can be takes a number of assumptions out of account by saying that the panel is being perfectly manufactured, which it may not be, and that all these panels, all these boards being put together will simply give an average of that result, which again is not the case. The second process, which is slightly more accurate, is a post-manufacturing process known as static testing. So static testing involves, you can see there on the left, a 4-point configuration where bending is applied at a constant rate and deflection is measured about the midpoint. From the bending and deflection data, we get a load versus displacement curve, as you can see there in the bottom left, which we can then use to find a slope to use in our stiffness calculations. So these static tests are accurate and effective in quantifying mechanical properties, although they can be costly, time-consuming, and at times destructive. Non-destructive alternatives are available for beams and boards, but no such system has been developed for the rapid assessment of CLT panels or any kind of wood-based mass panel. Furthermore, no NDE system is being used in Australia for the evaluation of CLT panels. So that leads us into the aim of this project, which has been really to research, develop and evaluate a NDE system for CLT panels for an inline rapid assessment within a manufacturing facility. So that really comes back to the main goal being to develop a tool that industry can use as their manufacturing panels as a quality assurance process to make sure that the grade they're aiming for is what they're pumping out. To do this, we investigated a number of sub steps. The first being to develop a evaluation program and method. From that method, and investigate furthermore the in situ requirements for these kinds of tests. So also the boundary conditions, which I'll talk about later on, and how they're going to perform in an inline environment in a manufacturing facility. From that, validate the experimental results we get from the first 2 points, compared against static testing methods as our control. And then lastly, investigate the theoretical and experimental comparisons between measured and predicted vibrational responses. So the method that we've adopted is something that has been similarly done in Europe by René Steiger in 2008, and we've refined it slightly to suit more of our applications, but the way that it goes is basically the same. It's a two-pronged approach where experimental modal analysis conducted at one stage using an accelerometer, vibrational-based, surface-based vibrational sensor, and an impacting hammer. Impacts are injected, excited along the panel surface, and acceleration data is collected by the accelerometer. Then processing that using a frequency response function, we get harmonic frequencies, which we can use to predict elastic properties. At the same time, theoretical modal analysis is the process of modeling these panels, so taking the panel's geometrical properties such as dimensions and weight to determine density, as well as some first initial guesses for stiffness of the panel. So if we take the targeted grade values for the panels, for example, and plot them into the system, we get a generation of modal responses and theoretical frequencies for how that panel is assumed to respond. And we then compare that against our experimental results, and it gives an estimation or a correlation between the two sets of data. From there, using an iterative process, we then vary the elastic parameters, or the first guesses that we had, until the error between the experimental frequencies and the theoretical frequencies is small. So for these tests, a number of boundary conditions were first going to be assessed as being useful, as we've found through literature. A number of different ways of restricting and supporting these panels was found to be not useful, but accurate. So looking into more deeply those types of boundary conditions, we decided to select 6 for our testing. The first of which being, and this picture considers 2 boundary conditions, one being simply supported and free, where the perpendicular edges are simply supported and the parallel edges are free, and then we alternated that, so to give a simply supported free and freely supported simple testing configuration. The third being a freely supported system. This one is a flat wires using suspension straps. This one is a simply supported on all edges structure, where the panel is situated on a timber frame that we've developed. Fifth one being again another freely supported configuration. We found through our research that there were a few different ways of supporting a panel freely supported, because while it is simple to construct these boundary conditions, the results vary between different kinds of configurations. So we decided to look into a few different ones. So we had the flat wires. This is an edgewise configuration using suspension straps. And finally, a third one being an airbag or air bladder configuration, where the pressure inside the airbags provides a nice dynamic response for the panel, almost as if it's floating, which is what we're aiming for. So the testing involves impact testing and accelerometer, as I discussed previously, FFT to find the frequency response, and then from that we get those plots. So we looked at the 6 different boundary conditions, and we got varying results for quality. The quality factor being the clearness of the signal, and found that the freely supported systems really stood out as being the most effective, and the airbag one being having the most consistent results in the dark black there, the FFF one. Yep. So the influence of shear was something else that we wanted to look at. So as the panels increase in thickness, the effect that shearing between the bottom and top layer will have on the result becomes more and more important to consider, which is an effect that some previous literature has assumed as being negligible, which we consider as being a reason why industry may not have already adopted a system like this. So the difference between the two theorem is consideration of shear deformation forces. So we've looked at the varying thicknesses of these panels and how the different theorem that we're going to be using affects these panels when they're simulated compared with our experimental results. So for the static testing, the panel, which is 3 meters by 2.4 meters, was tested. That was done in the previous stages. For static testing, we've taken a strip off of each end and applied a bending force to it, similar to the one of the first slides that I showed. So, there we go. So the results from those tests are quite interesting. So we found a really good comparison between all thicknesses on average for our between our NDE testing of the full size panel compared with the static results on stripped specimens of those panels. Everywhere from 75 millimeters to 120 to 115 millimeters gave around a 10 to 14% error. Results for 125 to and 150s are still being analysed, but show a similar trend. Starting to run out of time. So what's left of the project? We've still got a number of analyses to conduct in terms of shear modulus. So we've done a lot of experiments and validation for elastic properties in terms of stiffness. Shear is another big one that we really want to try and quantify with this system, as well as develop a more robust software interface between what's going to be the user in a manufacturing facility and having an almost fully automated processing system for them. So to date, this work's been presented at 3 other conferences, as well as we've have 1 paper almost being published through the second part of review, and 3 more planned. And we still have a final report and an operations manual to do. So there's a lot of work to do with the planned end of this project in a month or so, but we're quite hopeful. And thank you very much. Sorry that I'm going a bit over time, but if you do have any questions, feel free to get in touch with me. My email address there, my LinkedIn link. Yes, thank you very much again. Everybody have a good day.